Hey everyone, good morning. Can you hear me? Yep. Cool. So they lured you here with a Matt's keynote, and now you're stuck in a refactoring talk, which is pretty devious. I'm sorry about that. My name is John Pignata. I'm an engineer in New York at a company called GroupMe. And I want to start with a quick definition. Code smells are heuristics for refactoring. And the concept of code smells were first introduced by Kent Beck on Ward Cunningham's wiki in the late 90s, and then later more formally published in the refactoring book in a chapter Kent Beck co-authored. When we're building software, our design communicates to us through resistance. We may say things like, our code is difficult to understand, or to test, or to change, or to reuse. And this is the expression of that resistance. This resistance is really valuable. It's nudging us along to refactor. Code smells are hints from our software about how it wants us to reduce this resistance. And in this way, when we listen and respond to the hints that our software is giving us about how it wants to be structured, our design emerges from our system's parts. So the rest of this talk is going to be a lot of code. This is the system that we're going to be refactoring. It is a back-end API for a mobile application that's used by Google Android devices. The push daemon is the thing we're going to refactor. So the feature we're looking at is we deliver push notifications to users' phones. So like when someone favorites your message on Twitter, you get a push notification. That's what we're doing here. The component that actually delivers the push notifications to Android phones is this middle bit, the push daemon, which we've extracted from our application. And the push daemon is a little unorthodox. It listens on a UDP port. So it's listening for UDP datagrams. It takes those datagrams, extracts a message, and then delivers that message through HTTP to the Google API. Google then handles delivery of the message to the user's device. And just to give you an idea of this code as it was discovered, here it is. There's a lot of it, and we're going to go through it line by line, so don't worry about reading it. Hopefully it's somewhat legible. Let's just talk about what this thing does. So there's two externally visible behaviors in our push daemon. There's one command called ping, which is a simple health check. If we ask the push daemon to ping, it responds back with pong. And then there's a command send. Send is the central command of our system. It's the thing that delivers messages to Google's API. Let's test this thing. So in order to see how this thing works, we're actually going to run the script, and we're going to send it UDP messages and observe its behavior externally. So if we run the script, reading through the script, we see that it binds on a UDP port. In this case, it's 6889. We're going to run the script. It's going to block and wait for incoming datagrams. We could use netcat now. Netcat is a small Unix utility for sending messages across the network. And it has a -u flag, which means UDP. So we're going to send messages to our local host, port 6889. We're going to just type in ping and hit enter. It's supposed to respond back with pong, which it does. So our first test is passing, our first manual test. Next, we're going to synthesize a send command. Send is a little more complicated. So send takes parameters. So instead of just a command, send, we also include two parameters. The first is a registration ID. This registration ID represents a physical Android phone in the field. So an Android device registers with Google's API, and Google says, OK, here's your token. Here's how an application can address you. The phone then passes that token to us, and we use it to send it notifications. The second parameter is just some text. It's just some text we want to deliver into the phone. Since we're testing this as a black box, the only way we could be sure that this thing works is to send this message and use an actual registration ID of an actual Google phone. If we do that and hit enter, we then check our physical phone, and we get the message, so our system works as it is. And our second test passes. So we're going to be running this test a lot. We're going to be refactoring in many small steps. And we want instant feedback. We want to be able to run this thing in the background and for it to throw an alert at us if we break it. So we're going to write the outermost possible coverage. We're going to do the same thing we did with netcat and our eyes, but we're going to do it using RSpec. So in this test, we're cheating a little bit. Because our script body, we don't have an object definition. We don't even have any methods. We just have a raw script that runs. Because of that, we're going to use the Ruby load method to load the thing in a background thread. And we're going to then send it messages with RSpec and assert on the behavior. Now, we could fork a process instead of using a thread, but we're going to use a thread here because we're in the same process as the thing that we're testing now, which means we can mock and mock the Google API, for instance. So here's the first test. This is the same thing we did with netcat. Instead of using netcat, we're going to use Ruby. So we're going to say socket send ping, and then we're going to assert that the response should be pong. Same thing we did with our eyes, but now we're automating it. Here's the send test. Same thing we did with netcat. We're going to send in a prefab message, so send token with some text. But we can't automate physically checking a phone, right? And we don't really want to have to. We want to be able to test this as a self-contained unit. So what we're going to do is we're going to use webmock to mock the Google API, and our responsibility is just to hit the service boundary with the right parameters. So we're going to send in this command, and then we're going to assert that the right parameters come out. And now we could run the test, and the test passes, and now we could use auto test or something in the background to continue running this in the background as we refactor. So now we could actually start refactoring. We can go back to the original patient. Like I said, there's no class definition here, there's no method definition here, but our first code smell has to do with the fact that we have one long method. So it's a long method, it's not actually a method, but our script body is sort of the main method of our program. And this method is really, really long. It's 30 lines of code that's doing all kinds of assorted things. So let's go through it line by line. At the top, we're instantiating some collaborators. So we're instantiating a queue, an HTTP client, and a UDP socket. 3 things that seem to have nothing to do with each other. Next, we're actually creating a worker thread pool. So I assume we're using JRuby or Rubinius, like Mats just recommended. And we are doing this because we want to do some work in the background. So here we're using the queue to coordinate our work with the worker threads. Next, in the threads, we're actually creating a service request to the Google API, and we're sending them the data that comes down the queue. Finally, in the middle of the script, we're finally getting to binding to our socket. So here's our socket, and there's port 6889 again, just hard-coded in there. Beneath that, we are polling the socket for datagrams, so we're seeing if we have incoming datagrams. If we do, we're then dispatching a command based upon what's in there. If it's ping, we're going to go one way. If it's send, we're going to go the other way. And then finally, in send, we're doing all kinds of gross string gymnastics to extract parameters so that we could create this JSON body that Google expects from us on the other side. So to begin organizing this, we're going to need to break it down into smaller pieces. And our first move is going to be to replace this method with a method object. We're just going to wrap this amorphous script body in a method so we can give it some shape. So because we only have one method, we're going to create a method called pushDaemon. We have one object, sorry, not object. We have one object in our system, so we'll just use the same name as we saw in our diagram. And the mechanics of replace method with method object dictate that the first move is that we take the locals that are used in the method and we promote them to instance variables within the object we're creating. Next, we're just going to take the remainder of the script body and we're going to wrap it in a method called start. And then we're going to take the references we had to the locals and we're going to update it to instance variables so that we can use the instance variables we just created. So we still have our long method, at least now it has a name. It's called start. And now we could begin breaking that thing down into smaller chunks. So start is doing a lot. There's 3 statement bodies in start. We're spawning our workers in that first one. We're binding in the middle one. And then below, we're looping and processing incoming requests. So let's extract these 3 statement bodies into private methods. And let's leave references to these private methods in start so it's somewhat coherent. So we're spawning workers, which is just that same statement body. We're binding the socket, and we're processing requests. So here is pushDaemon with the private API collapsed post-extraction. And we still have a lot more extraction to do. But we have a choice. We can continue extracting into smaller and smaller methods, or we can look at pushDaemon as an object and see if its responsibilities make sense. I would assert that, in this case, pushDaemon has a lot of reasons to change. So here's a list of just random things that could possibly change about pushDaemon. The items in this list have only a tangential relationship with each other. And that's a code smell called divergent change. It tells us that if we have an object and the object has many reasons to change that seem unrelated, it's likely that the object has too many responsibilities. So we're going to extract objects from our pushDaemon object. We'll start with the worker, because the worker is pretty self-contained and it seems like its own concept. So our worker here is using the queue and using the client. It uses the queue to coordinate work amongst its worker threads, and it uses the client to post to the Google API. So we need these 2 collaborators in our new object. So we're going to extract an object called worker. Worker's going to have a queue and a client. We then go back to the pushDaemon, and now we can replace our queue and the client with our call to worker. So now we're instantiating a new worker, and that's going to encapsulate those 2 other collaborators. Next, we have to look through our code to make sure we're not using those instance variables we just nuked. In process request, we're shoveling stuff directly into the queue here, which we can't do anymore because we don't have access to the queue. But we do need some way to submit work into the worker. So what we're going to do is we're going to add a method to worker, the shovel method, to submit work into it. And this will just allow us to give the worker a piece of work to do in the background. We go back into process request and we flip queue to worker. Okay, so now queue is gone. Now we can actually extract the method we wanted to extract. So spawn workers is still in push daemon. We could move that method into worker now. So we're going to move it into worker. We're going to call it spawn because spawn worker would be redundant. And we're going to parameterize count. But other than that, we're going to leave it unchanged for now. In push daemon, we no longer call this local. It goes away. And instead, we tell our worker to spawn, and we give it some unit of work, unit of concurrency, in this case 10. Next step is this UDP socket, excuse me. So UDP socket, and we're using it a lot in this program. We're binding it to a port, we're receiving data through it, and we're sending data through it. So we're pretty concerned with the internals of this socket. And our object should be talking at a higher level of abstraction. We want to raise the level of conversation between these two objects. We don't want to be dealing with a low-level socket. We want to be dealing with something higher up. So let's create a UDP server. UDP server will expose a socket. It'll hide a socket, rather, the opposite. A socket's an implementation detail of the UDP server. Next, we're going to look at these three verbs, bind, receive, send, and we'll just give UDP server those capabilities. So we'll add three methods, bind, receive, and send, and it'll pretty much just wrap a socket for now. So we can go back into push daemon, and we can flip our socket to a server, and now bind goes away. We don't need this anymore. We just tell the server to bind. And process request, we have a couple references to socket. Those get updated to server. So we have another object now, but I would assert that we didn't achieve our goal. Our goal was to raise the level of discourse between these two objects. We wanted to hide the fact that we were dealing with a socket. And all we did was introduce another step in the chain. We introduced a middleman, essentially. We know a lot about how UDP server does its job. We know it uses a socket. We could guess that, but these details are leaking out of the UDP server. This is an example of inappropriate intimacy. We are inappropriately intimate with the internals of UDP server. And part of the reason is, in this sequence diagram, what we're doing is we're telling it to bind to a port, and then we're polling it to receive data. So we're constantly asking UDP server, do you have new data yet? Blocking, it comes back, it has data. UDP server can't really do much on its own without the push daemon kind of being its puppeteer. So we could rearrange these objects, though, in such a way where they sort of tell each other to do things rather than us asking it and forcing it to do things. We can create an interface where push daemon subscribes its intent that it wants to be alerted when new requests come in. So we're going to have a listen. We're still going to have to tell it what port it's going to use. And then we're going to tell UDP server, tell us when new information is available, and call a method on us. So let's go through that. So we have to update push daemon for our new arrangement. The first thing we have to do is, I mentioned we wanted to indicate our interest in UDP server to let it know that we want new requests. So to do that, we're going to pass in ourselves in the constructor. And the convention here is going to be, when you create a new UDP server, you pass in the application that's interested in new requests. Next, we don't know exactly where this is going to go, but we know we don't want to do this anymore. We don't want to pull the socket and get data from the socket. So we're going to replace that. We're going to just have a method called listen, and we'll figure out what that does in a moment. Next, these two things look the same now. Right, we're telling the server to bind, and then we're telling it to listen. Bind is kind of its own problem. We don't care what it has to do to listen. We just want to provide it a port number. So we're going to collapse those into one method call. Next, process request, the first thing it does is it asks the server, do you have any data? We want to decouple it from that. We don't want process request to have to worry about that. So we're going to add a parameter of data, and process request is going to assume that if someone calls it, you're going to have data for it to process, and we're going to promote it into our public API. So this will be the method that gets called by UDP server when there's a new request to process. Process request is a really bulky name that I don't really like, so I'm going to change it. I'm going to steal a convention from Rack and call it call. At first glance, it seems like process request is a better name. It's a longer name, maybe more descriptive. But I expect future developers who read this code will be familiar with Rack's API. So if they see call, they're going to instantly sort of intuitively understand the arrangement between these two objects. OK, next we're going to update UDP server for this new arrangement. So before we passed ourselves into the initializer of UDP server, so we have to change the method signature of our constructor. We'll do that. We'll add the app. Next, we have to update bind. So we changed its name to listen, and we added some behavior. So it still binds the socket. That's the detail of what it has to do to begin listening. But we also added this loop. So that loop that was in pushDaemon is now here, and it's responsible for polling its socket itself. And when it gets new data, it'll call our app with that data. So finally, back to pushDaemon. Most of our dirty laundry in terms of our private API is gone. But now we have this call method, which is a little bit of a disaster. The first thing that draws the eye is the fact that call is essentially a large case statement. And case statement was one of the canonical code smells from refactoring. It was the switch statement in Java. The thing that Beck and Fowler were concerned with was when you have a conditional like this, it has a tendency to proliferate itself in your code base. If you have occasion to check for a type or a type code or something like that, it's likely that you're going to do that in multiple places. I think our use of case is a little different. It's almost defensible. Like we're testing, we're looking at data coming in from over a network, and we're making a determination based upon that data. Something's going to have to make this determination. Something's going to have to say, is the command ping or is the command send? Whether it's a case or another structure seems a little immaterial. But our bigger problem is, in the branches of this case statement is a lot of behavior, and a lot of like really nitty-gritty like string manipulation behavior. And we can't unit test this stuff outside of the context of a pushDaemon, which feels completely wrong. So let's try to shake that behavior loose. We're going to want to collapse this case statement by making its branches identical and replacing the behavior in these branches with objects that quack to the same interface. So we're essentially going to replace this conditional with polymorphism. It's going to take a few moves to get there. The first thing we're going to do is, here's what the service does when it gets a ping. It sends back Pong across the network using this data stuff. We're going to extract that into an object. Because we have a worker concept in our system, let's create a job concept. Let's extend the metaphor. So we will create a jobs namespace, and we'll add a class ping. Ping needs data and server to do its job, so we'll just add those to the initializer. And then when we call run, it'll still send data across the network. And we go back to call, we take this statement and we just get rid of it and replace it with our jobs class and call run. So not a win at all. Now we have more code, but hopefully this shrinks soon. Let's look at send now. So we're going to do the same thing with send. We're going to forklift this out of pushDaemon and into its own job class. So send now, the semantics of send are such that the return value of run is a JSON string. So the semantics of send and ping are completely different. In ping, we rely on the side effect. We rely on the fact that when we call run, it's going to make a system call and send data across the network to the client. Run is actually just doing some string manipulation and returning some JSON. So we're kind of stuck now, right? We have these two branches that are different, and we can't eliminate this conditional unless these branches are the same. To make these branches identical, we have to zoom out and look at the larger system. We made this extraction before, this worker, and we just sort of like happily plunked all these Google API details in there. That seems really limiting now in retrospect. We have a concept of jobs and we have a worker. It would be much more natural if the worker could just work arbitrary jobs rather than being tied to the context of use of posting JSON to Google. So let's extract some of that dirty laundry. I'm going to take these details, these Google details, and we're just going to move them into send for now. So send is going to change a bit. Instead of returning JSON, it's going to do the post across the network. We're going to memoize an HTTP client instance. And send and ping now have the same semantics. When you call run, it takes an operation that does some unit of work, and we don't have to worry about the return value. Worker now is much slimmer. Instead of being tied to Google, this is now just a jobs runner. So it runs in it monitors this queue, and in each background thread, it pops off the queue. It expects jobs to come down that queue. When a job comes down, it just calls run on it. So that's the interface. Any job that speaks to this interface, we could use the worker to execute in the background. So now in pushDaemon, we no longer have to worry about calling run. That's worker's responsibility. And we no longer have to worry about the return value of send. So that all disappears. So now we have a case statement with pretty identical branches. The same, we have a different class, a different object there, but it's the same method being called with the same signature. And we essentially have a factory. So the case statement is just returning an instance depending on what command is sent to it. And then once we get a job instance, we just shovel that into the worker, and the worker runs the job in the background. So now that we have this factory, and it's clear that that's what it is we've had all along, we can move this into an explicit factory. So we're just going to copy it into a method. We'll add a method to the jobs meta class called factory, and it's just going to do the same work. So now we could finally think about, do we want to just get rid of this case statement? There's a compelling argument to get rid of it. If we keep it around, in future refactorings, it's possible that behavior is going to slip into these branches, and we don't want that. We want the interface to be standard, and we want all jobs to quack the same way. So let's make a move and get rid of it. We're going to go backwards a little bit to go forwards. So we're going to replace our case with a hash. The hash is a map from a command to a job class. In our factory, we get the incoming data from the client. We do some string manipulation for now. We then ask the class, we ask the jobs hash, do you have a class for this command? If you do, we instantiate it and return it to the caller. Now in our push daemon, instead of having this case, that slims down and we just call our factory, and the factory returns us a job, we shovel it into the worker. So push daemon has slimmed down quite a bit, but we've made a mess in these other extractions. So let's go and try to clean them up. Jobs ping, there's not much code here, but the code that is here is a little suspect. The first thing that we notice is we have these weird references to data, this associative array type structure. And we don't know what it is, but we assume it's data that we're only passing together. And this is a code smell called a data clump. So a data clump are two or more attributes that are passed around together to represent some larger value that can't be passed around individually, but do not exist in a higher level abstraction. So in this case, we have to look a little closer at what data is because it's kind of confusing. So this is what socket returns back to us. It's returning us two things. The first member is just the data that came through from the client. But the second is the structure called the sock adder. And the sock adder includes information about the client and some information about the network. And so protocol family, port, and IP address are what we're interested in. This is a pretty important concept in our system. We're a service that deals with remote clients. We should have a concept in our system, a home for this knowledge. So let's create that. We're going to create a client. This is going to be a very kind of, class isn't going to do much yet. It's going to take in the sock adder structure. It's going to use attr_info. Attr_info is a class in the Ruby standard library that knows how to parse sock adders. It's going to take that and decorate it with some methods so we can access address and port. Pretty easy. So now we get to clean up a little bit. In UDP server, we're just taking the data from the socket and throwing it to the app, like just saying, here, good luck. We're going to do something better now. We're going to deconstruct what comes out of the socket into its constituent parts, the message and the sock adder. We're going to create a new client out of the sock adder, and then we're going to call the app with client and message. This is a really good thing. We had a really terrible name hanging around for a long time, data, which is probably the worst name you could have in the system, right? What does data mean? Let's replace it. So now we can finally get rid of it. Data becomes its parts, client, and message, much more explicit. So now we can go back to jobs ping. We still have our data clump, but at least now our data clump is coherent. And looking at it, it becomes pretty obvious that we can't do this work without client's data. Client is the key actor in this line of code, but we are asking it questions rather than letting it do its job. This is an example of feature envy. We're trying to do someone else's job with someone else's data. It's obvious that client should be the one doing the work. Extracted objects tend to attract behavior. So now that we have something called client in our system, we want to give it behaviors. So let's do that. Let's let client handle sending the message. So to send the message, it's going to have to collaborate with a server. Server is the only thing that knows how to deal with the network. So we're going to add a server parameter here to the initializer, and then we're going to add a send method. So the send method is going to take in a message, Pong or whatever it is, and it's going to collaborate with server to send the message using the data it knows, address and port. Finally, in UDP server, because we're instantiating a client, now we have to pass in the server, which is ourself. And in jobs, now this collapses down to client send Pong, which is much better. Now we can deal with this signature here. We don't need a server anymore because client encapsulates the idea of a server, so we could stop passing that down. Get rid of that. OK, so let's turn our attention to send. So there's a lot of code smells in here. If we start at the top, we can kind of work our way down. So same name, different meaning. We have two concepts here with the same name. At the top, we have an HTTP client, memoized, that we're using to talk to Google. And then right below it, in our initializer, we're passing in the client that we just created, the service client that represents a requester. This could mean one of two things. It could mean that we've imprecisely named the actors in the system, or it could mean that this object knows too much. I think in this case, since we've moved around these details quite a bit, we start out in push daemon, then we move to worker, it seems like these need a permanent home. So let's create a concrete object in our system that represents a push notification. It's a pretty important concept. Push notification has a registration ID and an alert, and this object's behavior is it knows how to deliver itself to the Google API, and that's it. That's all it does. So now job send collapses, and instead of having to deal with the Google API directly, it uses push notification to do that. So we're left with two fairly stinky lines of code here. The first line of code is doing a regular expression match using capture groups, and the second line of code is using these pseudo-global Perlish, like regular expression side effect variables. We want to get rid of that. The first line of code is an interesting one. It's representative of primitive obsession. And this isn't to say that primitives are bad, right? Primitives are most of what we're passing around. But it's because we're using a simple type to represent a complex idea. What's happening in here is a complex idea. We're tokenizing the incoming message and trying to extract meaning from it. And we're doing it at a lower depth in our system than we'd like. If we zoom out, what we have between a client and a server is a line protocol. Our line protocol looks like this. We expect a command, ping or send, and then optionally we expect some parameters. These parameters have their own tokenization rules. So a parameter, a string, is split on spaces unless a double quote is encountered, in which case all characters enclosed in those double quotes becomes a token. This should sound familiar. This is exactly how the Unix-born shell parses parameters, right? When you have in the command line, if you put something in quotes, that becomes an argument. And that's what we've unwittingly built here. And the Ruby standard library actually has an object that knows how to tokenize strings based upon those rules. It's called Shellwords. Shellwords is something we can use to split up the incoming message into tokens and then use those tokens more intelligently. So we're going to create a new object. We're going to extract yet another object called request. Request is going to take in a message, and it's going to tokenize that message using Shellword split. It's then going to decorate it with two methods. We're going to have a method called command, which takes the first token and normalizes it into an uppercase string. And then we're going to take the remainder of the tokens, and we're going to return them as an array. And if we don't have any tokens, we're just going to return an empty array. So now things clean up quite a bit. Instead of passing down this raw message and relying on the rest of the system to kind of figure out what that message means, we're going to pass down a request. So here in our factory, instead of having to deal with a raw message and splitting it and figuring out what the command is, we're instead just going to use the request object to figure out what the command is and ask the hash to return us a corresponding job class. Finally, in send, we no longer have the regular expression and we no longer have the weird pseudo-global variables. We just have parameters, which is an array, and we're sort of binding ourselves to the position of those elements. Okay, we have one more piece of unfinished business before we're out of time. We've left Nil Checks scattered throughout the code in a couple of places. So the first place is in this factory. So we're saying, hash, give me a job that corresponds to this command. But if we pass in a command like info or shutdown or something like that, the hash is going to return nil to us. So we don't want to call new on nil because it will blow up. So we check to see if class is truthy. If class is truthy, then we instantiate the class and we return it to the caller. So our factory could return nil, depending on user input. Consequently, the push daemon has to guard here. So it has to check, did I get a job back from the factory? If I did, I'm going to shovel it into the worker. If I didn't, I'm not going to do anything. Nil is communicating an idea here. It's communicating the idea that an unknown command has been requested. And we can make this a concept in our system. We're going to use the null object pattern. We're going to introduce a null object to represent an unknown command. So it's going to look like this. It's going to quack exactly like a job, but it's a no-op. It's not going to do anything. You can call run on it. It's not going to do anything. But it speaks the same interface, which means in our jobs class, now instead of guarding here, we could use a cool feature of hash. So hash doesn't have to return nil as the default. It just does. That's its default behavior. We could tell the hash, when you get a key that you don't recognize, return null job. So now this hash is guaranteed to return something that quacks like a job. So instead of checking if we got a class back, we can just blindly instantiate it and return the instance. So in the case of ping and send, this method will return a ping instance or a send instance. In the case of anything else, it's going to return a null job instance. Now in push daemon, we no longer have to check for nil here. That can just go away. And this is better, but we've introduced a problem. Now we're enqueuing null job here. So null job's a no-op, but we're stuffing it into memory and making a thread grab it and call run on it, which is essentially a no-op. It would be better if we didn't enqueue it at all, if we short-circuited it here. And for us to do that, we have a few options, right? We could check the type of the job that comes back. We could say, if you are a null job, don't submit yourself to the worker. And this is just as bad as the nil check. I mean, it's pretty much the same thing. It's a little more explicit, I guess. It would be better if we inverted the dispatch here. So instead of the worker invoking the operation of the shovel on the worker, let's invoke the shovel on the job, because the job knows if it's a valid job that needs to be enqueued in the worker. So let's add the opposite shovel to our job. So we're going to add the right shovel here. The right shovel will expect to pass a worker in. In the ping job, if we get this method call, we're going to just submit ourselves to the worker for later execution. But in null job, we're going to respond to the same method, but we're not going to submit ourselves. Right? We're just going to no op. And that means the push daemon, in this case, we can just flip this. So job now goes into worker, and job can make the determination if I want to enqueue myself. So at a time, we're going to stop our refactoring here. I've put the code up on GitHub for anyone interested, for whatever reason. There's plenty left to do in the code. Like, there's tons of smell still left. Like, for example, we have hard-coded configuration details everywhere, and that's like the opposite of divergent change. That's shotgun surgery. It's possible that we're going to have to update those details in many different places when we deploy to a new environment, let's say. We also have weird boilerplate now. Like, to create the job interface, we have to add these methods. And it would be nicer if we extracted a superclass. But we don't have time to do that. And that said, even though we have some more work left to do, our push daemon is in much better shape than when we started. We listened and responded to the code smells in the original script, and we've made huge strides toward a more coherent design that will be easier to grow and maintain. That's all I have. Thank you guys for your attention. Appreciate it. Thank you.